Any questions, anything in the homework? All right. Yeah, the A and I think D are the same, are similar, right? So A is like list of timescales and compare it with polyethylene. Compare this polyethylene oxide. Huh? Oh. Oh, show a sketch of what each structure at each time scale. Yeah, all right. And then D is explain figure 4 using those time scales. So let's see. So I mean, one of the sketches is this, like this is the association of the lithium. I think the blue is lithium, blue sphere, and then these are the red things are these carboxyl groups. So there's a negative and that's positive, and they associate. Right, so that thing has a time scale in which it exists. Right. So it's like a short time. So basically, if you go to 4, so that short time is where this guy's got a negative slope, or the mean square displacement divided by t to the 1/2. So this thing is so he's got this idea that the mean square displacement, if it's Brownian, I should put it here, for diffusive, then that's proportional, but it's equal to 2 dt. So it's proportional to t to the 1. And then if it's sticky Rouse, then that's proportional to t to the 1/4, and then it's t to the 1/2 if it's Rouse. All right, so he plots this thing divided by that thing. That's his we call it the Rouse parameter. It plots the Rouse parameter against time. So if it follows this thing, then that should just be constant, which is in this. That should be this Rouse parameter, the number that you get for that. And then if it's following this thing, which happens if this thing happens, so this is called, both of these things are called subdiffusive. Because they're slower than diffusion, because it's going to a weaker power than diffusion would be 1. So the sticky Rouse is caused by that thing where you have the lithium plus thing, and you have these chains with the groups so that thing has a certain time scale. He calls it tau s, the time for that thing that it can exist on that. It exists for a certain length of time. He gets that tau s by, he figures out, this is a little vague, but he figures out the probability of, yeah, oh, sorry. Let's see, no, PC project. All right, so he figures out the probability that one of those associations exists. Like it's 100% if it's there, it's 0 if it isn't, but it isn't cut and dry, so it's got this probability that decays with time. I think he gets that from a simulation. So this you could also get from the NMR measurement that's in that other paper where they do a cross correlation, and you see the cross correlation peak. And the area of that peak would give you the probability of that thing existing, of that association existing. So you could take the area, say, of the carboxyls, and the area of the cross correlation in the 2D plot, and take the ratio of those two, would give you the probability that that thing existed. Out of all the carboxyls, so many of them would be in that state. So NMR can give you these numbers, and in the simulation, you just say, tell me how many of the carboxyls are this distance from lithium. If it's that distance or less, that's an association. So I take that as 1, and then if it isn't, it's 0. And I sum those up and get a probability. And I sum those and then divide by the total number of carboxyls to get this probability number. So that's how they get it from the simulation, I think. Anyway, so it decays with time, meaning that the thing has a lifetime. And he there's different ways. Like you'd fit this to an exponential like t over tau, and then you could get the lifetime from that. Another way to get it is integrate the probability. So probability dt, do that integral, and you get some kind of a lifetime. That's kind of like how you get a correlation length. You have two things and you say they're correlated or not. It has that decay function. So you do integral the thing times the derivative gives you the correlation length. This is like a correlation length approach to get tau. I don't know why he didn't just fit it with exponential, but this is how he did it. So he gets that tau. Maybe probably he did it because it agrees with T1. Now, so he gets almost a perfect agreement. Tau T1. So the plateau is in this plot of mean square displacement divided T to the 1/2. So there's a start and an end to it. So the T1 is when this sticky rouse disappears, which is when the lifetime of this thing, so those two agree almost perfectly. Again, it could be like how he calculated, he might have manipulated this a little bit, but basically they agree perfectly. So that's nice. And then, so that's the picture. Down here, you have this sticky rouse behavior, and then in here, you have the rouse behavior. So the picture, the cartoon of the rouse behavior is the bead and spring model. So you have, just have, so when you're in the middle, then you go to this thing that you have just beads and springs. And the beads are they have a drag coefficient that's going to be 6 pi the viscosity times the hydrodynamic radius, and the hydrodynamic radius we take to be r equals n to the 1/2 L, like a Gaussian chain radius for some. So you have a chain. Okay, and then you're gonna like kind of coarse. So in computers they call it coarse graining. You're gonna say, well, I don't want to look at every carbon in here. I'm gonna say like I'm gonna take that thing, right? And in fact, this is from like 1953. So this is the first coarse graining before computers were invented. So he's talking about coarse graining, and also this is the first idea of something like a blob, which is the topic today. But so in 53, these ideas already kind of existed. The difference is that the Rouse, this is called a Rouse unit. It doesn't have any physical size, like there isn't a physics to what the size is. You pick some size that's big enough that the Gaussian equation will work, but not the whole chain. So there's any number of different sizes of a Rouse unit you could pick. Right, so it's a little bit more flimsy than the later ideas of a blob where the size is fixed by physics. So anyway, so in coarse graining is kind of similar to this. You just pick a size that's going to be convenient for your simulation that you can say predict what the properties of the thing is. This is almost exactly the same as coarse graining in molecular dynamics or in Monte Carlo. You can do it in any of the kind of methods of, it makes it, instead of doing a billion calculations, you end up doing 50. Because you divided a billion by whatever you get to get 50. And then the question is, did it work or not? Then you coarse grain less if it didn't work. If it worked, then you're done, right? So basically, this is an idea of coarse graining that he brought up in 53, which is good. And it's different than that's different than the Debye model, which doesn't have coarse graining in it. Debye is actually looking at every atom. But the Debye model is the same thing, it's beads and springs. And then the math of it, to get the Debye relaxation time or the heat capacity from the Debye method, it follows the same math as what Rouse uses to get this tau as the largest vibration. So once you set it up like that, so for Debye, this is a crystal. So he has atoms in a crystal. So it makes sense. They're in a straight line and they're going to vibrate. So if you just look at a straight line of that, they're going to vibrate like a guitar string. In other words, this is called a transverse wave, and there's also let's see, transverse and longitudinal waves, right? This is a transverse wave like what we're used to. Longitudinal wave is a sound wave, so it packs up. In other words, the density fluctuates it's like an accordion. So the things in that accordion tightness is like moving through the material. That's a phonon, right? So that's like how sound propagates. Right, so you can have transverse or longitudinal waves. You can study them in the same way. They can have the same kind of behavior, like a modal. So if you have a guitar string, then it's got the first order mode and the second order mode, etc. And all the energies kind of in that mode. That's like the main thing you hear when you strum the guitar. But there's these other overtones that exist, higher frequency. Right. So this material is going to have the same. I mean, by the Rouse model, you end up with this kind of idea. This first order Rouse mode, that tau s is proportional to the molecular weight squared. That's kind of the idea that he gets from this. So anyway, so that said, like if you want to draw a cartoon, it's like this cartoon of the bead and springs. And you should say like the friction factor is that. And then the spring constant for this is R3 KT over NL squared that we had before. So the N is the Rouse number that he arbitrarily picks, some number that's smaller than the whole chain, but bigger than a mirror unit. So that Gaussian statistics applies to it. Then you do a force balance on that. So you say the force is the velocity times the friction factor, and then it's going to be plus the spring constant. So the distance that the spring moves times the spring constant, which is that thing. Then you add in a thermal fluctuation that kicks it so it moves. Like this is going to be proportional to KT. And it's going to be a delta function that happens every now and then and makes the thing move. Then the velocity is dx dt, and this is x. So you have a differential equation, you solve it, you get an exponential from that. And the exponential would have this tau s as an argument in it, basically. It's like t over tau s is kind of what you'll get. The tau s will be like the viscosity or the friction factor divided by the spring constant. Or if it's in mass, it would be, so the friction factor is going to be like the viscosity by the modulus. Anytime because the dynamic one has time in it, like shear rate, right? And the other one's shear. So you get time out of that if you take shear rate versus a shear, and you end up with time. So the viscosity is proportional to this relaxation time. Friction factor is proportional to it too. And that's kind of how you end up with this n squared thing somehow. So anyway, so that's just a picture of that. But the cartoon of it is like this bead and spring thing. You should mention that the characteristic of a bead is that it's got a friction factor, and the characteristic of a spring is that it's got a spring constant, and they both go back to the polymer thing. Right. And then so anyway, that's the cartoon for within this entire region, and the things that are changing is you're adding modes to it until finally, so you're adding the smallest mode, so the highest frequency, and then which would be 1 Mur unit. So that there are limits to it because you have the entire chain, which would be the lowest order mode, and the highest order mode would be like 1 Mur unit shaking. So you have a wave where you have single Mur units, and each one is a wave, right? So that's called the in the heat capacity, in the Debye heat capacity, that's it's the limit of reciprocal space, which is called something. I don't remember the name of it. But basically, when you do a diagram of this kind of thing, you plot it in Q instead of in real space, and the high end of it is this limit of the size of an atom. That's the most you can vibrate. You can't have phonons that go smaller than an atom. So basically you have a limit to this space. And this has a limit of the space, which is a monomer of the chain. So just lifted this thing that Debye did that was kind of complicated and totally unique, then plopped it into polymers. I mean, the interesting thing is that the Debye model is a bead and spring model, and then you look at the polymer and you go, oh, that's a polymer. Like Debye never thought like that's a polymer, but he drew a picture of a polymer with beads and springs. And then later on, like 40 years later, Rouse came along and said, oh, that's a polymer. Right. And then didn't cite Debye when he did his thing either at all. Like in the paper, in the Rouse paper, there's not a mention of the Debye heat capacity, and he's doing exactly the same thing, So it's pretty strange the way that paper is, I think. But anyway, so you got this bead. So here you have this sticky Rouse, which is a picture, or maybe even this picture, right? It shows the lithium and it's attached to the 2 carboxyls on 2 different chains hooked together, makes a cross link. And this is where that times out, so it doesn't exist anymore if you wait long enough. And then you start exciting the Rouse modes, so that the ones that are one monomer, and you keep exciting until you get to the total chain, the single vibration for the whole chain. So this is where, that's where you just see that. Then after that, the chains, then again, you don't see that stuff anymore because you're timed it out. You've gone to a time longer than that thing exists, so it doesn't exist anymore. Once you go to such a long time, so these are kind of constraints, like the chain is constrained by this crosslink. Then if you wait long enough, that goes away. It's like the silly putty will eventually make a puddle. Then it's a liquid and it doesn't have that network structure, so you can ignore the network. And then here you kind of can start ignoring these different modes of vibration until finally you get to the last one, because then you can ignore the entire idea that it's vibrating inside. And at that point, you've waited long enough that it's just at that T1 point, you've waited long enough that it's just so you started that it's hooked together, then it forgets that. Then it gets to, oh, I have these vibrations. I can do this vibration, I can do that vibration, that one. Finally, I get to just that one. And then, oh, I can forget that. Then finally, I just have the chain, which is basically a ball, right? And it's just moving around till it hits something other ball or something like a gas atom or whatever, and it goes another way. And then it's just going like that. So the cartoon, that's what diffusion's, it's got a mean free path. I think it's usually like that. That whatever that symbol is, psi or something. So the mean free path. So like a gas atom would have a mean free path until it hits another gas atom or something else, then it takes a sharp turn. That's going to be literally, this is the same thing as our persistence length. It's the same thing, right? And you're going to match it up to get by the same root. You do an exponential minus the distance over that thing to get, and you see a decay function in the position of the gas atoms, and you get that kind of, so all the math of this persistence length comes from pre-gas kinetic theory of gases, right? The idea that you have steps. So you can say, well, it's just going to be like that. So it's just something moving around like that, and the thing is like the chain, polymer chain. So that's a cartoon for the other end of it. Then in that region in between, you kind of get that thing, and early on you have the lithium here, like that holding it. I think that's it, like 3 cartoons probably is good. That's T1 or tau S, and this is T2 or tau. He calls it Rn because this guy depends on n squared. So you have to have an n here. It's dependent on how big the chain is, because you reach the end of the chain when you get to the final thing. But that time depends on n. This time doesn't depend on n. It's like a mirror unit time, mirror unit vibration or something, the small scale one. So anyway, the cartoon, hopefully that kind of helps a little bit. It's, yeah.
And can you go over sketching the log time plot?
Showing the 4 behaviors in figure 3. Okay, so yeah. So this is something that came to me, that like, why are they even doing this? Like, why are you even plotting it this way? Because, all right, so this is like in the old days, they didn't have computers, and then you'd have to plot to linearize something. So yeah, you'd plot like this thing to find that plateau part. It's like when you plot I versus Q, you get a power -1 for the persistence part, but you could plot IQ and it would be flat. You could say, oh, it's flat, it's persistence. So it's kind of more obvious than a power law slope. But so these are all power laws. So if you, I mean, so we have 3 power laws or something. 3 power laws, right? So you have 3 power laws. You want to distinguish between them. Like nowadays, since you can make log plots pretty easy by pushing a button on your computer, you just say log scale, right? And then you'd find out that you have these slopes. So you have like 1/4 slope, and then you'd have 1/2 slope. I did that too steep, and then I did it too steep. So 1/4 would be almost level, then it would be like 1/2 would be a little bit steeper, and then finally you go to 1, or +1. Right, so you could just see, I mean, you could just see the regimes then. You could see all 3 of them in the same plot. You wouldn't have to worry about, oh, is that really like at 1/4, and is this really like 1? And also, you can see that this implies that something is decreasing and something is increasing when everything is increasing. So this is misleading to do this kind of plot. All right, and sometimes, say we had a transition in slopes where it went 1/2, 1, 1/2, right? Well, or 1/4, 1, 1/4. Say I had that. Well, what would that look like in this plot? It would be like, let's see, 1/4, 1, 1/4 would be like, oh, I have a peak. Like I would generate a peak in the plot. And then when you see a peak, oh, it's got a half width and it's got a position. But neither of those numbers have any meaning. They just arise because you made the stupid plot. Right? You plotted it in some way, right? So it's much better to start with the real stuff and see what's going on rather than trying to go to these other plots. Because they can lead you to, and this is pretty common, like people will do this. You'll see this in papers, you know. So you have it, I mean, I know from scattering, so log I, log Q, so you have -4, which is like a clump of something, like some goo, right? So, and then you're looking for, like, say you have sheet structure, so it's gonna go -2, and then it'll go to -4 again, right? So this -2, there's a thing, it can either be called a Kratky plot, or it can be called a Lorentzian correction. So you do IQ² versus Q. It's similar to what he did, right? And then you find out, oh, at -2, that's flat. And at -4, it comes down like that. And then it goes -4 again like that. But if you have, say, if you have persistence in here, like -1, then this thing will go like up and then down again or something like that. And then people will like look at this thing, and literally they will take that peak to have a meaning of size, and they'll take the width of it to mean something. So you can't just, like, this kind of plot is kind of messed up. There should be a peak in your original data if there's a peak in the data. You know, there's not, generating it isn't really a good way to get it. You know, so anyway, so that said, that's something to keep in mind, I guess. Anyway, so did I answer this? That's what, yeah, so you just get straight out the slopes if you did it that way. And then you wouldn't have to worry about what is this really 1/4, or is it not 1/4? And is this really 1 or not 1? Like you would see like what it is instead of trying to figure it out in a plot that isn't meant for that. So
Would the carton A that compare this ether or polymer to the polyethylene oxide?
yeah, I didn't do that. Let's see. Okay, so see what does it say? List the timescales and then compare it to crown ether. Yeah, I didn't actually look at that, but because this is the standard bearer for this kind of polymer electrolyte, like not a liquid electrolyte. So polyethylene, because it's cheap and it's like everywhere, so everyone uses it. So, but the thing is, he mentions in the paper, that's why he says it makes a crown ether thing. So you have carbon, carbon.
Swap it over.
Yeah, all right. Sorry. See, in this case, you have a lot more oxygens, so they're weaker. It's a weaker connection, right? So this is a lot less del negative than this guy, because this guy has a resonance structure where it can go actual negative charge. Forget about del, and then double bond C. So it can flip like that. It can go single, and it can do it 2 ways. So this is actually really a negative charge. So a lot more attraction and potential for a lifetime in that thing. With this thing, you have the lithium, and the idea is that one chain, at least his idea in the paper, is that the one chain forms a crown ether around it. So it's going to be like that, like it ends up looking like a crown. You do it in 2D. In 3D, maybe this is different, right? So, I mean, there's actual molecules that are shaped like that, or different sizes, and they fit different ions in the middle, right? But in this case, we have a polymer, so it's gonna go off like, but this, he's saying one chain would be sufficient in that because the distance between all these oxygens is enough somehow to make it, and it's a flexible chain. So this oxygen, the OC bond is like the most flexible, rotationally flexible bond. So basically, it's easy for it to make kind of rings. And the carboxyls, because it's got resonance structure, it has to be on a plane. So this, all these atoms in that bond, those all have to be coplanar because of the resonance. If it's got resonance, it can't go off a plane. Like a benzene ring is a planar, just a planar structure. Right? It's got, it resonates like that. Whoops. So anytime you have resonance structure, you're gonna have a sheet of paper is what the thing is, right? So this thing's a lot less flexible than that, so it can't make a ring around it. So it's stuck with just hooking two together. So I guess, is it asking for a cartoon of this? I mean, that's kind of the cartoon, like draw a crown ether, but have the chains able to dangle off somehow. Again, this is in 2D space and it's actually in 3D. So it's going to be a lot easier for it to kind of curl around and have the chain fly off. And here it looks kind of awkward that those two are together, but, and it could wrap more than once. And it could be like a ball and it's just woven all around it with a chain, you know. I mean, I don't think that's determined, but basically that's kind of the crown ether thing. I think that's what it's asking, right? I just put it in there because he mentions this is an alternative material, and then why is this stuff better that he's using? So he went to the trouble of, this is synthesized. This isn't like a commercial polymer, you know. So they made this intentionally to do this. So I think they're thinking that this cross-link thing has an advantage in holding the structure together. Yeah.
So for A, question A, there's the sketch with the structure for each of the time scales. Is that the thing that we were talking about earlier, where
Yeah.
like it starts vibrating a lot at T1 and then like it stops vibrating by tau2?
Yeah, so at the low end, you have his picture. I mean, he's already drawn it for you, the first picture, this thing. So you have the chains and that sticks. And then but that has a lifetime. Then that lifetime ends and then that thing doesn't exist. It's like the silly putty. If you wait long enough, it's a liquid, it won't bounce, you know, because you waited so long. So the bouncing part doesn't exist at that time scale. So this thing doesn't exist when you get past T1. Right?
So it stops at T1.
Right. This thing doesn't exist anymore after T1 because you waited so long that this thing doesn't have any effect.
Gotcha.
Yeah, so it kind of exists, but it kind of, in the time scale you are, it's gone before you can look at it.
Right.
That's there, proof is gone, you know, so it didn't exist really. Right, and then you get to this point where you get to Rouse, and that's going to be these modes, and they have different times. So the shortest time is going to be the highest frequency vibration, which is a thing that's a monomer. Each monomer is one of the nodes of the vibration, right? And that's similar to the it's called the block diagram. Let me just Google it here.
So the most intense vibration will go away first.
Yeah. Let's see the thing I want. Yeah, no, not intense. The most intense meaning in magnitude. So intensity means amplitude, right? So the most highest amplitude vibration is the last one. That's the Rouse mode. The entire thing is one mode. That's the tone you hear on the guitar, right? The E string, right? But if you touch different parts of the string, you get different tones. Like there'll be actually higher frequency E's, and the highest frequency E is when you touch the kind of, I don't know what bar it is, but it's way up high on it, and you hold it and you just touch it and it goes like ee. I don't know, it's at the top of the guitar, not the fully top, but there's, I forget what thing it is, but
Like is it like on one string? Or
yeah, on one string.
yes, like the very end, either like the end of the guitar or like
No, right up near where you're plucking it.
Oh yeah, we're like really high chords.
Yeah,
like
and if you just
20%.
barely touch the string there and pluck it, it'll make this ee.
Yeah.
You know,
Okay.
so that's the highest one you can get.
Okay, so the
Right.
highest frequency.
And that in terms of, if it's atoms in the Debye model for heat capacity, that's one atom like shaking, and that's the peak of it. And it doesn't matter if you get smaller than that. If you get smaller than that, the modes overlap with the higher order mode, so you get a higher tone than what you had there. So that's the one atom one. That's the highest frequency you can get. And here it's like it's 1 Mur unit.
Okay.
That's the highest frequency you get. So you're coming down from you're getting into the Rouse area, then you get that thing. That's when you first start the Rouse behavior. Then you go up to longer and longer times, and then it's going to be that big one, the entire string, which is a main tone. That's where all the energy goes.
Okay.
All the energy is stuck in that big one. And the other ones, you can't exactly hear them with your ear because their amplitude is small. And when you play it, like you wouldn't do a power chord on that, because it would be like,
Yeah.
"Ee!" It'd be like a Mickey Mouse or whatever, the Chipmunks power chord,
Yeah.
I don't know if you ever heard them, but so anyway, so you don't get the amplitude with it. The amplitude's all in that lowest order, and you can calculate this. There's math that goes with this to calculate it. You can calculate the energy in that mode, and that Rouse mode is like 85% of the energy, the largest mode. So you're going across that flat part. Finally, you get to T2, and that's the Rouse mode, and then you've reached a time where all those other Rouse modes are like that thing that was the crosslink thing. It doesn't exist anymore because you're at times that you've waited it out. You've waited so long that those things don't matter. They don't make any difference. And then then the thing is just as if it's a frozen ball that's just diffusing around space. So the picture is just this kind of step thing of a particle moving around, the diffusion model, where it has a mean free path, and then that makes a random walk. And that gives you that the distance squared goes with 2 times the diffusion coefficient times time, so power 1. So you're from 1/4 to 1/2 to 1.
Okay.
These are all like constructs, so you can't, when you see the stuff, you'll see it like people will have like 8 power laws or something, and like, so not 8, but 5, I mean, like Colby does this with Polymer, with polyelectrolytes. If you look at those papers, and it's like, at some point, it's goo, and you can't take it that seriously, but basically if you want to, so you have to kind of take this a little bit of a game. Like, on the other hand, Debye's prediction of heat capacity is really important at low temperature. It's like, so you solved a lot of problems with it at low temperature. I think it was cited in his Nobel Prize and stuff, So in one sense, you shouldn't take it too seriously, but in another sense, it's like kind of important for some things. So anyway, that's kind of that thing. All right, so anyway, what do we got? All right, so that's it, I guess, for this. It's a pretty good paper, I guess, for this thing, I mean, I think that the interesting thing is that, anyway, yeah, so anyway, I think that the fact that they kind of superficially zip over that this equation is only good for the last stage, like the Brownian motion stage. So all the other stages with subdiffusion, this equation doesn't work, but
Can you go over the susceptibility for engagement?
yeah. All right. That's a good thing. So this also goes back to the heat capacity stuff. So it's kind of, I mean, I think it makes sense because they're all talking about vibrations, it's for phonons or these kinds of vibrations of molecules. So it's kind of similar. So this thing, all right, this is called the partition function. Okay, or the Zusammensumme, I guess in German. So it's the energy sum, so what he does is he takes the sum of the energies and he divides the scattering, which is kind of the amplitude of energies. And from that ratio, he gets the susceptibility, which is how the magnetic field energy or electric field energy is absorbed by the material, like the spectrum of energy absorption. So it's got to do with this kind of quantification of energy levels. So he wants to take his spectrum and make it into a plot of kind of a modulus, or how it absorbs energy versus frequency. And then in that, he wants to get the components that make it up. So it's a way to separate the components. You can see it's just a smeared out curve, but he's saying it's composed of these kind of Gaussian. They aren't Gaussian, they're 1/, they're symmetric about the peak. So it's 1/1 plus the frequency squared times the time squared. gives you this kind of shape of a thing. So anyway, there's functions that describe that. So if you can break it into these individual and you have an idea what the individual are, you do a simulation, you can get the individuals, you can pack it into this and make up the one that you measured, which is just this curve divided by that function, you know. And that thing comes from it's in the notes for oh, and I didn't fix the links. I didn't fix those links here. I should do that, but it's kind of too late. I forgot to fix those links. Anyway, somehow we got back to this thermo class, but basically it's all in this heat capacity thing. And there's books that go with this too in here, but let's see, that's PowerPoint. This is the thing I want. And then, oh, don't I say like where to look? Say something here. Homework, and it's like thermo 33 to 7. It's not much of a, it's like a pretty broad range, but all right, this is a good place. So this 1 minus e to the minus x, and x is beta h nu e is our guy. That's like beta is 1 over kt, and h nu is kind of our guy. Let's see, what did I just do with the thing that I had? Not that. Must be here. So anyway, that thing comes from, does it say here where it came from? This comes from this, like summation of exponential e to the minus n. Then you say, actually this slide 17 is a good place. So this geometric progression, summation of something to some power from 0 to infinity, and there's infinite energy levels. So that's appropriate. Then that thing equals 1 over 1 minus x, and x is the exponential of minus x, and x is our beta h nu e. So that ends up giving you this 1 over 1 minus x thing. When you multiply it by the energy, this is a probability, the Boltzmann probability of an energy h nu over kt, like the probability that you have a certain energy level. So anyway, when you do that, if you divide that 3, you get through the e to the minus e to the whatever minus 1 from that, if you do that right. So that like this down here, e to the minus 1, that thing you get from just that ratio, which is this is the sum of states, the sum of all the energy states in the system. So so for whatever reason, and I don't know how you word that into the answer, but basically that's the sum of states. This NB is just the sum of states. So that's the number. If you take the log of that, you get the energy for the system too. So it's kind of like, so anyway, this is something that if you took advanced thermo, you'd get that. You don't get it in undergrad thermo, right? But advanced thermo, you get that. So basically that's in here. I mean, you can glance at it if you want. There's a bunch of books in here too that kind of go through that. But anyway, it's kind of worth noting that that's what that is. So they're just using kind of advanced thermo stuff to get the thing to look right so they can do the fit. And the fit's going to be that frequency fit. That's probably in here somewhere too. But it all kind of ties back because heat capacity is vibrations, and it's kind of got to do with the same kind of molecular vibrations. So it's all in the same can of worms. Oh, I can find the name of the thing I'm looking for here. Here, this is the thing I'm looking for. It's like this A would be the atomic spacing. So pi over A is the limit because it's one atom shaking. And this is an inverse space. K is the inverse space wave number, right? So if you go to 0, so this slope in here is the speed of sound in the material. And then you get to a single atom, and that's where it ends. That's called the block diagram. And then oh, these are Brillouin zones. Yeah, so that's the end of the Brillouin zone, which is where you get in inverse space, you get to 1 atom. Right? And then so you can't get any smaller than that. And there's different ways to look at that. Like if you look at the vibration, so this is if you look at the vibration smaller than that, it ends up, you can transform it into a larger size vibration. there's somewhere here, there's a video of that happening. I guess it wouldn't work in a PowerPoint and a PDF. Anyway, so yeah, so there's that thing. Actually, this actually gives exactly that factor. This is slide 28. So it just does kind of what I was saying and does it. It gets that thing. That's the one we're using right in here. Yeah, that's it. So slide 28 has it. This is what this is like a bunch, the same stuff from a bunch of different books. So I don't remember what book this is from, but anyway, so if you're interested, there's books in here. I don't think anyone's interested, but basically there's a bunch of books, thermal books kind of here. This stuff is like Kittle's the place where that's like the basic book. Kittle and Cromer or Kittle alone somewhere here. Those are like the base. Dove is a good one for that stuff. There's 2 Dove books. This is the original Kittle. So I don't know. It's a whole field in itself, but basically it's touching into this, so we kind of have to mention it. Especially that Rouse stole the Dubai thing. Like you can see, let's see if I go back. Where did I put that? Let's see. I just had it. I did something. Capacity. Oh, here. That's what I want. There. It's like 73. That business. I mean, you'll see that the picture of I gave the slides. Oh, it was 33 to 7. Yeah, so that's the Dubai model. Like this is exactly the same thing. Beads and springs. You just add them up. This is exactly the same math that's used for the Rouse. This is that differential, the velocity, the acceleration. Let's see. Anyway, so this is kind of like the differential equation that you solve and you end up with kind of an exponential thing or cosine wave, and it's got a lowest order mode where all the energy is. It's the same story. Basically the same story. Even if you look in Rouse in the Strobel book, he has this picture and he calls it the Rouse equation, And this is strictly the Dubai thing. Anyway, so it's kind of interesting. All right, so what do I got? 52. So anything else on this stuff or yeah? Oh, because, all right. That's a good question. So what's the wrong paper? Is this the right paper? No, that's not the right paper. This. So this guy, I mean, all right, the way I see it, it's not clear, okay? But basically the way I see it, this is going to, if you say you're at a fixed time, so time disappears, then this is just Guenier's law. It's like R squared Q squared over 3. I mean, there's something about 2, this thing's 2 times dt or something. So somehow this ends up being Guenier's law. If you go to, that means there's some size. So Guenier's law is for a kind of a cloud-like particle that doesn't have a surface. So it doesn't have a surface. If you expand it, it doesn't have a surface term in the expansion. So basically it has no surface. So it's just a Gaussian function with no end for the structure. All right. So anyway, so it has to be some kind of particle, and the particle he's talking about is a monomer. And he's saying that the monomer is 10 angstrom. That's where he gets the using 0.5, Q of 0.5. Because he's doing this in a backscatter arrangement. So he's not doing a scattering experiment like shooting the beam straight through. He's shooting the beam at the sample and taking the pattern backwards. So, and that's to get high Q. Q continues going beyond 90 degrees. It goes all the way to 180. Right, so if you want to get high Q, you go to backscatter. So you shoot the beam through, some of it bounces back, some goes forward, and then so basically you can put a detector on the back side and get the high Q part. That's usually used for crystallography. So 0.5 is let's see, I think one is something like 15 degrees or something, 2 theta, and then this is going to be like 8 degrees. Let's see. Oh, it depends on the wavelength too. Anyway, so he's in backscatter. He's got 0.5 inverse angstrom, just about 12 to 13 angstrom, I think. 2 pi over that. So you get smaller sizes at high Q, but he's saying 0.5 is a large size. And for the backscatter machine, it is large because it's going to go up to like 10 10Q or something, you know? So basically 0.5 is pretty small for him. It's big for us. Like for us, we're looking at 0.001 usually to look at polymers, 0.001 to 0.01, right? So he's looking at 0.5. It's like much smaller. So he's at 10 angstrom size. He's saying that's 1 mer unit. So he's saying he could kind of get a Grenier function at that size, which you don't see because it goes to persistence, right? So you don't see a Grenier there. You see power 2 and then power 1. So there's no like me thing. So it's a little odd what he's doing. I think he's just picking off a size where you could see a monomer, like a whole monomer. Yeah.
Why don't you recommend to use this?
Yeah, because you wouldn't be looking at a particle, you'd be looking at the scaling of it or something, or you'd be looking just at the surface of it. If you go to higher Q, you'd have the particle, and then if you zoomed in beyond the size of the particle, you'd just see the surface. So you'd be looking at surface dynamics maybe, or something, whatever's happening with the surface. If the surface is fixed, you'd see nothing, I guess. It should just be stuck. In this case, I think the surface would just be fixed, or you'd see the atomic vibrations of it at the surface, maybe, or the, I don't know what you'd see. But basically, he's going to 0.5 because he thinks that's the size of a monomer.
So it's like a resolution.
Yeah, like you're looking at the motion of things, what things are you looking at, and you want to pick a size that's the size of those things. So if you wanted to look at the size of this room, you do 2 pi over whatever the size of the room is, and you go to that Q. You know, but if it's a monomer, it's 10 angstrom. He claims that. So that's the Q that he goes to look at monomers moving. That's, and then if you go to higher Q, you wouldn't see the monomer anymore. You'd be zoomed in so far. So you'd see something else, like the surface of the monomer. I guess that's what is left there to look at. And if you looked at lower, so I guess the monomer moves with the chain, so you see diffusion of the chain, even if you're looking at the monomer, if all these other vibrations are gone. Pretty confusing. I mean, I don't think it's that straightforward. I don't think if they understood it, they wouldn't be using this function to model subdiffusive motion, you know? So, and then, so especially when it's time to the 1/4, like such a weak, it's so far from diffusive that it probably doesn't work there. So anyway, so yeah, you can, that's that thing. Anyway, anything else on this? Okay, all right, so all right, so I wanted to start going through this stuff today. Maybe I can begin it a little bit. We got 5 minutes maybe. And this is kind of the last part of well, I might just go through the Rouse model like a little bit better, so that since that came up, and maybe we should go through a little bit the math of it, you know, a little bit. But so I might do that, but basically this is the last thing, and then there's topical things after this that we could do. We could probably vote on it. Like I have some notes on membranes. I think people wanted to talk about membranes. So we could do that, yeah.
I saw that you posted the final, what will it be? Do you have an idea yet?
Usually it's the last, whatever the last week is, and then one other random thing. It's like 2 questions, two normal homeworks. One's like the last week, and one's whatever random thing. That's the traditional way. So, and then it's individual. So it's actually a lot of stuff to grade, but I might back off on it. It might be too much to grade, but anyway, because we got 30 something in here, so it's a lot, but anyway, I can do it though.
And I assume that since it's double homework, basically, we just complete it the same way we would a normal homework, except individually.
Yeah.
Yeah.
You can work together.
Okay.
I mean, but basically, yeah, turn in an individual document. But if you want to group up, it's fine. Like you should know everyone in the class at this point, I guess. So find the smartest person, like group with them or something. But you can ask questions on it too, whatever, you know, it doesn't matter. But I guess what, maybe since we got like 5 minutes and this other thing might take more than that. Let me just see what I got and also get suggestions if anybody has anything they want to do. So I have notes on membranes here somewhere. Rouse, I have nano composites. I have all that stuff here linked up, huh? That's weird. Dubai stuff. I didn't realize that. Rouse. So I probably will go a little bit through Rouse. Then I got a whole set of slides on machine learning and artificial intelligence in polymers, which I could, and then nanocomposites I have. And then somewhere I did a whole thing on membranes in here. So, and I could do something else too, if you guys have something you want to do for the last weeks, doesn't matter. I can make up some other stuff. But, like we could do bio things or something, or I don't know. Anyway, think about it. After this week, I'll probably go to something else, I guess I'm inclined to do machine learning and artificial intelligence. And someone said early on that they were doing work with membranes, because like chemical engineers, there's like several groups doing membranes in chemical engineering, so it might be worth doing that. But I'm not sure, is there a class in membranes? There must be. So this might,
Organic. But it's at the same time as
oh,
this.
oh, is it? And who's teaching that?
I don't know.
Oh, okay. All right, so, all right, yeah, maybe I'll just do that. I mean, it's just like with membranes, just have the molecule absorbs and then it transports. You have the two things and you figure out how that fits together. There are physics people working on that. So, and it has to do with batteries and things. So we can probably do that. And then I think that machine learning, artificial intelligence is probably worth doing something just on that because it's so important now. It's like, and I might bring in a speaker for that too. So anyway, yeah, why don't I guess we can quit there. So yeah, so I hate to let you go before 5 minutes after. It's like something seems wrong about it, but anyway, why don't we quit early? Yeah.
Membrane machine learning is
Oh, good. All right. Because I looked around. All right, because I looked around and everyone's like, what's like, I don't want to do that. And it's like,
about battery stuff.
oh yeah, and we were gonna do a molecular dynamics thing too, right?
Okay.
Yeah, so like do a lamp simulation. So we can do that. That's actually like 3 weeks then. I think that's what we got. So to do machine learning, membranes, and some kind of molecular dynamics thing. So mostly it'll be just like almost like a workshop, I guess, doing this one thing. So that sounds good, I guess.
Yes.
Yeah.
Team for the figure three.
It's just Brownian motion, Brownian diffusion. So that goes with time t, and then that's going to be like it's basically the kinetic theory of gases, right? You have the gas atom, it just bounces and it goes like jogs around. And it's hitting other gas atoms, hit it, make it move around. So that's basically
Was
diffusion.
that the one?
That's where it goes to 1, yeah. So this mean square displacement goes with 2 times diffusion coefficient times time. So the power 1. Yeah. 1/4, 1/2, and 1. Yeah. So no, there's only 3. There's 4 because you have there's 3. I think there's 3, yeah. So, all right.
Thank you. Good day, Professor.
You too, yeah. See you guys later.